Here we're going to do a couple of problems that deal with forces from electric fields. An electron of mass m, charge magnitude E, and initial velocity v enters a region between two oppositely charged plates, equidistant from each plate by a distance x. Here comes this electron down from the bottom, right down the middle of these plates, and you can see up here at the top, the distance is x to each plate from the initial undeflected straight line path. And the electron collides with one of the plates at a distance y. So it doesn't make it all the way through. It collides right here with one of the plates. So let's draw electric field lines into this figure. Electric field lines go away from positives and towards negatives. And what would the trajectory of the electron be? Well, the electron is going to be attracted to the positive plate and repelled from the negative plate. So that electron, if it hits right here at a distance y, it's going to go boop, just like that. What's the electric field magnitude between the plates? Well, we know what the charge is. We know what the mass is. We know the initial velocity. We know the distance x, we know the distance y. So if we know what those are, what's the electric field magnitude? Well, let's see if we can make head or tails out of this. I'm thinking that the force that this electron is going to feel is going to equal its charge times the strength of the field, which we don't know, but the charge is little e. So we've got that much. Furthermore, Newton's second law says the force should equal the mass times the acceleration. And this is an acceleration, isn't it, in the x direction? If we look at this figure and if x is horizontal, then this is an acceleration only in the left-right direction, which means that we can solve this for the acceleration in the x direction as being little e times big E divided by m. So that's one thing we can get from this. What else can we get from this diagram? It looks to me like the distance y is numerically equal to the velocity multiplied by the time that this electron is between the plates. When we don't know what to do, let's do something. What else can we decide here? I think the distance x, this is analogous to a horizontally launched projectile that is in a gravity field and it bends down. Obviously, it's turned at 90 degrees. But the displacement in the x direction for a case like that should equal the initial velocity in the x direction multiplied by time plus 1/2 times the acceleration in the x direction multiplied by time squared. In this figure, this distance delta x is merely x. There you go. Now you can see that at the top of the page. That distance is x. The velocity in the x direction initially is 0, so I can cross that off. And then we just found an expression for ax. So I think what we've got is x is equal to 1/2 times the quantity little e times big E divided by m multiplied by t squared. Now, we don't know what t is, but we do know here in the y direction that t is what? Y divided by v? If there we put y squared divided by v squared, what does that leave us with? That leaves us with x is equal to little e times big E times y squared divided by 2 divided by m divided by v squared. Let's check off what we know here. We know what x is, we know what little e is, we know what y is, we know v, we know m. This should do it. The electric field then should be found as what? 2 big M little x little v squared divided by little e little y squared. Let's try another one. Here we have a negatively charged object that's in a gravity field, and it's suspended by a string, and it's just sitting there. And there's an electric field down here, and we want to know in what direction the electric field points. And that would be to the left. The electric field points directly in this direction. And the reason for that is that negative charges are forced opposite the electric field. So you can see that this negative charge, you can tell by the tilt of the string that this negative charge is experiencing a force to the right. Therefore, the electric field must point to the left. Now, we don't know what this uniform electric field magnitude is, but we want to try and find an expression for that. So let's see if we can do that. Let's draw a free body diagram. There's our charge. We're in a gravitational field, so mg is going to act straight downward. Then we have the rope, which has a tension, kind of like that. And then there's an electric force on this electron pointing that way. And the electric force is equal to the charge times the electric field. And the charge here is given as Q, and the electric field, of course, we don't know what that is. We don't know what E is. We actually don't know what T is equal either. But we do know that this thing is at rest. And so everything is in equilibrium in both the y direction and the x direction. So if I put coordinate axes here, that might help. Let's do the y direction first. And do we have a theta in here? Let me scoot up to the original picture. There's a theta. Theta is the angle made with horizontal. In our free body diagram here, there's theta right there. In the y direction, it looks to me like t sine theta will be numerically equal to mg. Mg and theta are all known, therefore tension is going to be m times g divided by sine of theta. That was one of the things we were asked to find. The other thing we're asked to find is an expression of the magnitude for E. Now let's sum the forces in what I've called the x direction, and we're going to go Q times E in one direction, and isn't that going to be numerically equal to T cosine theta? Well, we just figured out what the tension is. T is m times g over sine theta. Can we solve that for E now? I think we can. Is going to be mg cosine theta. Cosine theta over sine theta is cotangent theta, so I think we're going to get here m times g divided by little q multiplied by cotangent theta. Cosine over sine is cotangent theta. Theta is known, m is known, g is known, and q is known. There you go.